Hi everyone, we'll be starting class in about 1 to 2 minutes time. Alright, afternoon everyone. Basically, our schedule for today is that we'll be doing 2 lectures. The first lecture is going to be lecture 8, which is poles and zeros. The second lecture is going to be on the initial and final value theorem. And afterwards, we'll be doing the selected questions from problem set 1 that everyone voted on. And I'll be doing the top 3 questions that had the highest responses in particular. Afterwards, I will post up the solutions for problem set 1 on my learning. And if there are any other further questions regarding the problem set, you guys are free to email me accordingly to ask these questions as of such. So let's start with our first lecture today, which is basically going to be poles and zeros. Now, given that we have a proper transfer function where the degree of the denominator is more than the degree of the numerator, once this condition is satisfied, it is possible to factorize the polynomials of the numerator and denominator. So that means we could just factorize the numerator and denominator accordingly, and we could get it in terms of multiplication factors. And a good example of this would be where we can actually extract out an actual gain component. 1 second, guys. Hopefully that mitigates the noise. There's some construction going on next door. Alright, so what this means is that when we factorize the numerator and the denominator in particular, we are able to obtain a constant, if it's possible, and then we can get factors on the numerator here accordingly and on the denominator. Now, these factors are also referred to as roots, because if you actually ever factorize a quadratic equation or a cubic equation, those roots here basically indicate that when the entire equation is equal to 0. So the roots on the numerator are basically referred to as the zeros of the transfer function g of s. And the roots on the denominator are referred to as the poles of the transfer function g of s. If you are able to factor out an entire constant here from the numerator or the denominator accordingly, or both at the same time, this is also referred to as the overall system gain. So for a general example here, if we have g of s here is equal to 3s plus 12, all divided by s squared plus 2s plus 5, we can factorize the numerator here such that we get s plus 4 accordingly, and we have 3. So in this case, the 3 here would be our system gain. And then we can factorize the denominator accordingly, because this is a quadratic equation. And we can use the quadratic formula in order to obtain the roots. And as such, we can obtain the product that will form this equation here. So in this case, our denominator will factor to s plus 1 minus 2j and s plus 1 plus 2j accordingly. And because these are considered roots, and the numerator are zeros and the denominator are poles, the 0 of the entire g of s system would be at s equal to negative 4. So we basically say s plus 4 here is equal to 0, and then we find out what the value of s is. And the poles here, in this case, is going to be minus 1 plus or minus 2j accordingly. Now, because we have zeros and poles in this form, it's possible to plot this on an imaginary versus real axis plot. So I realize my axis is not labeled here, so I'm going to write that in at this point. Oops. Right. So basically, the dot here represents our 0. Because we saw that our 0 here was at s equal to negative 4. But there was no imaginary component for it, so it just lies straight on. But the imaginary component will be 0 here, and the real component would be minus 4. Our poles, on the other hand, had real and imaginary components. And basically, we knew that the real component of that would have been at minus 1. And then it was plus or minus 2j. And the poles here are mapped by x's. So when you're doing a pole zero plot, accordingly, the 0 here is mapped by a dot, and the poles here are mapped by x's. we have a question in the chat asking why is 3 the system gain? Right, so these basically are factors of S here, and then we have a constant accordingly that is factorized out, and we can just pull this constant out the entire equation from all the factors. And as such, that would be the overall system gain. And the reason for this being the system gain is that if you ignore this 3 here, that means all of these components here are basically multiplied by a factor of 1. So whatever contributes towards the 0 here and the poles here accordingly in the overall system, it's just going to be scaled towards that factor of 1. But because we have a factor of 3 here, that means everything here now scales by a factor of 3 accordingly, as of such. So when I say everything is scaled by a factor of 3, that means the entire system here, g of s, is now going to be scaled by a factor of 3. So this is why we refer to it as a system gain. Alright, so just to recap a little bit, zeros are mapped by a dot on the imaginary versus real axis, and poles are mapped by x's on the imaginary versus real axis. The imaginary axis is on the y-axis, and the real axis is on the x-axis. And this is how you draw a pole 0 plus accordingly. These poles here, because they basically they have one real component and one imaginary component, it's basically referred to as simple poles. They are more complex poles in nature in mathematics, but we will not be dealing with those. We will only be dealing with simple poles and simple zeros. Alright, so let's say we have an example here, and we need to find out what the poles and zeros are for this entire g of s system. Now, typically, if this comes as a question in exams, because the denominator here is an order of 4, we tend to give you like 2 hints to give you an idea. Okay, you have these 2 poles already, and it's a lot easier for you to find out what the other 2 poles are because you have this hint here. So, for the interest of time, I think yes, I did solve it on the next slide. In the interest of time, it's possible to use auto factorization tools while you're practicing. It's also possible to prove that you obtain a pole or a 0 by doing random substitution as well. Both methods are basically okay. Unfortunately, in the exam room, you won't have an auto factorizer. In this case, because the exams are going to be online, and most likely you will have access to the auto factorizer, but you are still required to show an indicator of how you obtain the poles and zeros accordingly by showing that you actually substitute these values in and you got the entire equation equal to 0. So you just can't be like, okay, these are the poles upright. You actually have to show working to say, okay, the entire equation is equal to 0 and these are the poles henceforth. So because we have the hint here for the 2 poles, s equal -1 and s equal -2, that means it will be s plus 1 plus multiplied by s plus 2. So the denominator here will now be s plus 1, s plus 2, and then we have the remaining factor here. And this remaining factor here, you know it's going to be a quadratic. Now, you can obtain this in one of 2 ways. Like I said, if you have the auto factorizer, it will do it for you immediately. If you don't have the access to the auto factorizer, that means you're going to have to multiply out this part here accordingly. That means you'll get s squared plus 3s plus 2. And now you're going to have to take this in particular here and divide it accordingly by the entire denominator here. And when you do that, then you'll obtain this part here in particular. And then you can factorize out the entire equation accordingly. In some cases, you're lucky enough that you can substitute values for s and you can get it out immediately. In some other cases, you can't, but because the exam is most likely going to be online this year, you will have access to an auto factorizer in some form or fashion online, so it'll actually shortcut the work a lot for you. You just need to just prove that these values here are actually the zeros and the poles accordingly. So if we actually plug in the autofactorizer for that equation, we basically can see that the poles will resolve to -1, -2, and then -3 plus or minus j3. And the 0 here, because it's a quadratic equation, we can just basically use the quadratic formula, and we can solve for this, and we can see that the zeros will resolve into 2 plus or minus j4 accordingly. So if we actually put this on a pole 0 plot, so I'm backtracking here for a little bit. Remember the zeros here are 2 plus or minus j4. So the real axis here, this will be at positive 2. And then because it's plus or minus 4 on the imaginary axis, we'll have the first 0 here at 2 plus j4. And then the second 0 here at 2 minus j4. And then for our poles here, which are -1, -2, and then -3 plus or minus j3, we basically have at -1 here, represented by our x for our first pole, -2 here for our next pole, and then at the -3 part, we have plus or minus 3 accordingly for the last two poles as well. So this here will be -3 plus j3, and this one will be -3 minus j3. And that basically is the end of how you actually achieve a pole 0 plot. Once you obtain the roots, you just basically map it out on the imaginary versus real axis here. And once you put that in, that's basically the end of the question for anything regarding pole 0 plots. Now, in some cases, you may be given the pole 0 plot and you may actually be asked to do the reverse to obtain the actual transfer function. And it's basically just the reverse of what we did. You just read off the poles and zeros accordingly from the plot, and then you put them into root form, where you basically take the values and you transfer them over to the left-hand side, and you just multiply out accordingly. Or zeros will be on the numerator, or poles will be on the denominator, and then you can just basically obtain the transfer function at that point. And once you have that, you can basically do the inverse Laplace transform, because at that point, you can, if you don't want to expand, but you are required to get the time domain, you can just leave it in its multiplication form or the roots form, and then you can perform partial fraction accordingly. Once you have the answer in partial fractions, you can then use the Laplace lookup table to do the inverse Laplace transform, and you'll obtain your time domain equation. So let's actually watch a general example here. So let's say we have a y of s transfer function here, with 7s squared plus 18s plus 20, all divided by s squared plus 5s plus 6. And we basically need to factorize this out accordingly, and then perform partial fractions, and then do the inverse Laplace transform in order to obtain the time domain equation. So in applying the partial fraction technique here, we notice that the first thing that we do is that we need to make sure that the degree of the denominator must be more than the degree of the numerator. And in this case, we can see here that the degrees are the same. And because the degrees are the same, this doesn't satisfy the condition for partial fractions. So as of such, we're going to have to divide the numerator here by the denominator once and obtain a remainder in order to then perform partial fractions on this remainder itself. So to give you an idea of how we actually do this long division, I'm going to do it on the side here on the slide, so that way you can actually see how to do it. So we basically say it's going to be s squared plus 5s plus 6, which is going to be our denominator. And then we say this is going to be 7s squared plus 18s plus 20. Now, once we start this for long division, we need to make sure that the numerator and denominator are in descending powers of s. So they must start with the highest power of s and then descend accordingly as of such. When performing the division, we basically watch this here to say, okay, the first step of the division is that we watch the s squared here, and then we say the 7s squared here, which is the first component of each of the numerator and denominator, must be divided. So we say 7s squared divided by s squared here will give us a result of 7. So that result of 7 goes here. This 7 now multiplies out accordingly by this part here. So that means it's going to be 7 by s squared, so we get 7s squared, 7 by 5s, which is going to be plus 35s, and then 7 by 6, which is going to be plus 42. Because this is basically long division, that means we have a minus sign here. So 7s squared minus 7s squared will give us 0. 18s squared minus positive 35s is going to be 18 minus 35. So that basically is going to be minus 17s. And then we have 20 minus positive 42 here, which is going to give us a result of 20 minus 42. It's going to be minus 22 here. So as of such, this 7 here is now mapped to this 7, and the minus 17s minus 22, if we pull out the negative sign, we now get, so if it's minus 17s minus 22, this comes like if we pull out the negative sign, we get 17s plus 22. So this part here goes here. And because this is basically the remainder, it still needs to be divided by this part here accordingly. So that's how we actually obtain that condition to satisfy partial fractions. Are there any questions regarding this method before we actually go on towards the partial fraction theory? Alright, so once we actually satisfy this condition here, so such that you have the degree of the denominator here being more than the degree of the numerator, so I'm actually going to have to fix this here. Yes, do I have to fix that? Let's make sure, backtrack a little bit. Okay, I'll check back this to make sure, but in this case we're basically saying that the degree of the denominator here needs to be more than the degree of the numerator. So I'll fix this slide if the terminology here is wrong accordingly. Once we satisfy this condition, that means now that for this part here only, which is our remainder, we can actually perform partial fractions on this accordingly. So in doing this, if we factorize the denominator, this means that s squared plus s squared plus 5s plus 6 will factorize to s plus 2 and s plus 3. And then, in doing this, that means we can then perform partial fractions accordingly to obtain each one of these components. And the components here will basically resolve to 29 and minus 12. Now, because the exam is online this year, you also have access to auto partial fraction solvers as well, which you can find online. And this actually will help you obtain your partial fraction components immediately as of such. But for the purposes of exams, you do still need to write out your working accordingly and show how you actually obtain to these answers here. So please make sure that you show your working when you're doing partial fractions. There will be a very clear instruction at the start of all the exam papers. Please show all working. So pay attention to that accordingly. If you just put the answer directly, you most likely are going to lose out a lot of your marks. So make sure you actually show your working. So we have a question in chat that we do this when the numerator is more than or equal to the denominator. Yes, basically. So once the degree of the numerator is more than or equal to the degree of the denominator, you cannot perform partial fractions. you need to make sure that the degree of the numerator is less than the degree of the denominator. And once you have that, then you can perform partial fractions accordingly. I know in particular that we will have a slide later on that basically shows us a very optimized way for how you can actually solve partial fractions. And if it's not in this slide, it basically will come down, or in this lecture, it will basically come down in a later lecture when I basically show you guys how to do a very optimized way to solve for partial fractions. I think I actually can show you one way how we can solve for this as well. So, because we know here this is going to be s plus 2 plus s divided, s plus 2 multiplied by s plus 3 accordingly. Let's say we wanted to find for the s plus 3 component here. So let's say if this was A and this was B. To solve for A, we basically say 17s plus 22, which is the numerator on the left hand side here, divided by the component that is not s plus 3, so this is going to be s plus 2, and then we substitute in this part here with s plus 3, so we basically say that's equal to 0, so s needs to be minus 3 here. If we do this substitution, we basically will get a value of 29. And I'm going to pull up a calculator just to make sure this answer is correct. Yep, so the answer is correct. I just not verified it on the calculator. So yes, this is actually a nice optimized way for actually how you can solve partial fractions. And basically, what I did here is that I took the numerator here, I left it as is, and say if I was solving for A here, this means that if we are solving for A, we're going to be multiplying accordingly by all the other factors here on the denominator except for this factor. So we have the 17s plus 22 here, and then because A is associated with the s plus 3 factor, we put all other factors here accordingly on the denominator. So the only other factor here is s plus 2. And then, because we're solving for A, for the A factor here, we want to know when the denominator here is going to go to 0. And for that, we need to find out the value of s for that. In this case, it will be s plus 3 is equal to 0, so s is equal to negative 3. Once we have that, we substitute s equal to negative 3 here accordingly into our equation, and then we can actually solve for A equal to 29. Oh, and just to clear up some confusion here, because I've seen my labels are nearby to each other. Similarly, if we wanted to solve for B, it will still be the same numerator, 17s plus 22. The B factor here is now, that's s plus 2, so we put all other factors that are not associated with the B factor here on the denominator, so in this case it's going to be s plus 3. And then we need to make sure that we substitute in the value for s associated with the B factor here when this denominator here goes to 0. That's going to be s equal to negative 2. And as such, we'll get B here is equal to minus 12. And you can actually verify this using your calculators or some sort of online MATLAB or Octave or whatever else you fancy. You basically want to get the same answer here accordingly. So once we have our values here for A and B, and then we can put this accordingly throughout the entire equation. But remember, our equation here had this negative sign. So we then map this accordingly back into our equation here in partial fraction form. We can then actually perform the inverse Laplace transform to obtain our answer in the time domain. So if we compare this with the lookup table, we basically see here that our 7, which is basically a constant here, will just map to delta of t here, and it will just be 7. Our s plus 3 component here and the s plus 2 component here basically maps to the e to the minus 80 components. Whereas the constants here, being 29 and 12, they just basically transfer over accordingly with respect to the transform. So any constants with the Laplace transform basically remain the same accordingly. And all the other components here, be it that if it's a constant, you'll have this transfer into delta of t. In this case, because you have the s plus 3 and the s plus 2 roots here on the denominators, this will transfer to e to the minus at, where the a here will basically be this root factor here for each one of these. And as such, when you actually do the transform, we can see here that the 7 will transform to 7 delta of t, minus 29 divided by s plus 3 is going to be 29 e to the minus 3t, and the 29 basically transfers here accordingly, so this will be minus 29 e to the minus 3t. And similarly, for this part here, we basically will have 12 e to the minus 2t. And that's actually how you obtain your final answer accordingly with respect to this. So are there any questions regarding the inverse Laplace transform accordingly as of such? Because it basically, you have done this already in mathematics for engineers, so this basically is a recap, and if there's anything unclear, it's pretty advisable to ask any questions now. When is it b? Okay, so I have a question here asking when it be a minus between the fractions. Let's go back one slide. Let's go back 2 slides actually. When we expand up this brackets here, it's going to be 7 minus 29 divided by s plus 3. But this minus sign is now multiplied by this minus here accordingly. So this will be plus 12 divided by s plus 2. So this is actually how we get 7 minus 29 divided by s plus 3 plus 12 divided by s plus 2. Alright, so got a few questions here in chat, so I'm answering them in order of difficulty. Dirac of t is basically delta of t, because this is basically the common form of delta in Greek. So you can say Dirac of t or delta of t. And someone asked for the shortcut for partial fractions. Alright, so I'll redo this so you actually can see how this was done. Alright. So basically, because we have our left side here, and we're basically factorizing the denominator here, sorry, into these factors. When we actually want to solve for partial fractions, let's say this one here was A, this one here was B. We basically keep the numerator as is, and then we watch the factors here for A and B accordingly to figure out how we actually want to map our equation. So if we're solving for A here, we basically say A here is equal to the numerator that we have here, is 17s plus 22, divided, and now that means we're going to have to consider what factors are not associated with this A here. So as of such, because we have A here associated with the s plus 3 factor, our denominator needs to include all other factors besides this s plus 3. And the only other factor here is s plus 2. So that's why we put s plus 2 here accordingly. Because we have this resultant equation here, and we're solving for A, we need a value for S to substitute. Since we're solving for A, this A factor here is associated with S plus 3. We need to find out what the value of S is going to be here for this denominator to be 0. So S plus 3 is equal to 0, so we get S equal to negative 3. Because we know S is equal to negative 3, we substitute this value here into our equation for A. And once we substitute s is equal to negative 3 inside here, and you actually can do the calculation on the calculation on the calculators, you'll get A here is equal to minus 29 divided by minus 1. So you get 29. Similarly, if we are solving for B, we use the same numerator, and then the denominator needs to be factors that are not associated with b. So the only factor here is s plus 3. And then we still need to substitute a value for s here in order to solve for b. So because we're solving for b, we want the value of s here on the denominator when it's equal to 0. So this way here was going to be s plus 2 is equal to 0. So this will be s equals to negative 2. And once you substitute that in accordingly, you get b is equal to minus 12. Right. Any further questions regarding the partial fraction theory part that may be a little bit unclear? Alright, I don't think there are any further questions regarding the partial fractions part. If there are, we'll come back to it. Alright, and just right. The further on the question regarding the Dirac of t function, the only time when we actually put Dirac of t is when we have a constant by itself. So because we have the 7 here, when we do the inverse Laplace transform, we basically say 7 Dirac of t or 7 delta of t. But because these factors here are associated with Laplace transform from the table, in this case it was e to the minus at as of such, and we have those constants, we don't really bother to put the Dirac of t function accordingly for these constants, because they're already associated with the transform here accordingly. So it's okay for these transforms here to just be minus 29 e to the minus 3t and then 12 e to the minus 2t. But for a constant by itself, then you actually put the Dirac of t function here accordingly. Alright, so I actually have a little bit of homework for you guys to do and for you guys to actually attempt as your own practice problem. Basically for you guys to actually get a little bit familiar with the auto factorizers and the auto solvers that you may be able to find online, be it on Desmos, Wolfram Alpha, a couple other websites who actually have these as well. So try to find the inverse Laplace transform of this function here and actually practice it out and so forth. And I will basically give you guys a solution to give you an idea of if you're on the right track. But I'm not going to give the solution right now. By next week's lecture, I basically will give you the solution for this accordingly. So one thing to note, to know if you're on the right track for doing the inverse Laplace transform, if the roots of the denominator are real, basically like if there's just s plus 3 and s plus 2, when you do the inverse Laplace transform, it's going to be in the form of the exponents here accordingly, where m and n here are basically constants. However, if the roots of the denominator are complex, meaning that it's going to be like s plus 3 plus or minus j3 or something, like of such, the inverse Laplace transform is going to be in the form of e to at cosine of bt, and e at sine of bt accordingly. So for real components on the denominator, it would just be the exponents out accordingly. And for imaginary and real components on the denominator, you want to have the exponent cosine and the exponent sine components accordingly. Okay, we have another question here asking how much is a question like this is going to be worth in an exam. If a question like this comes in the exam, it's basically going to be worth somewhere in between 8 to 10 marks out of the total 100 marks of the exam. And the marks will be distributed accordingly for showing the working how you obtain the roots, especially if the roots are complex in nature. It will also be distributed how you actually perform the partial fractions and how you solve for your constants in the partial fractions, and then actually performing the inverse Laplace transform correctly for each one of those partial fractions. So it can be anywhere between 8 to 10 marks accordingly out of the total 100 marks for the entire exam. Alright, so that's the end of basically the poles and zeros lecture. Are there any further questions regarding the material in this lecture? Alright, so if there are any further questions, we'll be moving on to the next lecture accordingly. Close this off. From such yet, on to this lecture. Right. So this lecture here is going to be focused on the initial value and final value theorems that actually can be used to calculate the values at transients or initial conditions and the values at the final or steady state conditions for a particular system. And in order to do this, that means we need to have the Laplace transform system equation or basically our transfer function to evaluate these values in particular. So a nice property of the Laplace transform is basically we can analyze certain time behaviors of an entire system without actually having to go back into the time domain. And in some problems, in particular, we only care about the initial or final values. And for our purposes, the initial value will be the transient value, and the final value will be our steady state value. And all this evaluation actually can be conducted using the Laplace transform. And in order to do this, we use two important theorems, which are basically known as the final value theorem and the initial value theorem. So before we actually do this with respect to the Laplace transform, we actually need to visually observe how this actually occurs in the time domain. So if we have our y of t signal here, being an exponent multiplied by a cosine signal, and we actually obtain a graph for this, we basically see that the wave starts at some very small value, but then it keeps on oscillating and gets out of control. So as time moves towards infinity, the entire y of t equation will never converge to some finite value. It just keeps on oscillating and keeps on going huge and huge as of such. However, if we had e to the minus 3t instead for this cosine, this comes like if we just reverse the entire signal accordingly. So if we actually plot out the signal, we start with a huge oscillation, but then the oscillation dies off and approaches a steady value as time moves towards infinity. As of such, we say basically that the y of t here can converge to a finite value as t approaches infinity. Let's say if we mitigated the entire exponent value here, because we know anything to the power of 0 is just going to be 1, that means we're just going to end up with the cosine here. And because that's a trig function, it's just going to keep on oscillating forever. And as of such, we never converge to a finite value as t tends towards infinity. So, because we observe this with respect to time, let's actually observe this with respect to the Laplace transform instead. Let's say we had some system transfer function here, g of s is equal to 1 divided by s, all multiplied by s plus 1. And the questions that asking is that we need to find the steady state value of g of t. We want to be using the Laplace transform instead of going back into the time domain to evaluate this. So the equivalent of t approaching infinity of g of t is similar to the limit as s approaches 0 of s multiplied by g of s. And the reason for this existing with respect to limits, remember time is inversely proportional to frequency. So t is equal to 1 on f. And s here basically represents frequency. So as t approaches infinity, that means s here in the frequency domain will approach 0. If t approaches 0, s will be the converse and will approach towards infinity instead. So for our example here for the final value theorem, we want to know what happens when t approaches infinity. So we say limit as s tends towards 0 instead. And then to evaluate this, we say we must have s component here multiplied by the g of s system transfer function. So in applying this to our math here, and we substitute in g of s accordingly, we see that this s here and this s here basically cancels. And as such, we are left with the limit as s tends towards 0 of 1 divided by s plus 1. If we substitute in that limit for s tends towards 0 into this s value here, we basically will get 1 divided by 1 resulting in an overall value of 1. So this actually will give us the final value for our entire system of g of s. If we wanted to verify this, we can perform the inverse Laplace transform on g of s and we can obtain our g of t equation here. And then we can say as t tends towards infinity, you evaluate the limit, this exponent function here basically just goes straight towards 0. And as such, g of t here will just evaluate straight towards 1, showing that the mapping does exist for the two of them. So just to recap, the final value theorem is evaluated in the Laplace transform by saying limit as s tends towards 0 of s multiplied by g of s. So let's say we had the same g of s equation here now, but now we want to observe what is the initial or transient value of g of t. So this is where we make use of the initial value theorem instead. So the initial value theorem is basically the limit as t tends towards 0 of g of t, and because t is inversely proportional to frequency, that means it will be the limit of s tends towards infinity. Excuse me for 1 second. Alright, sorry about that. Had to answer the door there for a moment. Alright, so yes. In evaluating the initial value theorem, this basically has limit as t tends towards 0. And inversely, because t is inversely proportional to frequency, this is going to be limit as s towards s tends towards infinity of s multiplied by g of s. If we substitute our g of s here accordingly into our equation, these s's here basically cancel. And now we're left with the same condition as before when we were solving for the final value theorem. So we'll have limit as s tends towards infinity of 1 divided by s plus 1. If we substitute s equal to infinity here on the denominator, that means that we now have 1 divided by some really huge number. And that means basically, for the limit evaluation, this entire thing here would approach towards 0. If we verify this in the time domain, we basically know that when t here, for the limit t tends towards 0, is substituted in here as 0 for the exponent, this is going to be 1 minus 1. And as such, we get a resultant value of 0, showing that the mapping exists for the initial value theorem as well. So to recap, to solve for the initial value theorem with respect to the Laplace transform, this is going to be the limit as s tends towards infinity of s multiplied by g of s. So just a little more homework for you guys to actually do some self-practice. Try finding out what is going to be the steady state value of the output of the system here. So that means you're going to be evaluating it for respect to y of s. And then see if you could calculate the steady state value by a step change of 5 units mapped as x of t. That means you're going to have to map this x of t here into x of s and then evaluate the steady state value accordingly as well. So try doing this as homework for practice and see if you actually can obtain an answer. I will give you guys the answer at the start of the next class accordingly for this problem. Alright, so that basically is the end of the initial value and the final value theorem. One thing to note in particular is that if you see that your numerator and denominator when doing the evaluation limits tends towards infinity, that means that something is going wrong when you're doing the evaluation. And in some cases, it may be advantageous if you divide the numerator and the denominator by the highest power of s in the entire equation. This actually will help you to evaluate the limit a lot easier as of such, and you will actually obtain a finite value. Someone in chat might actually know what is the actual guy who does that maths thing in particular. I think the Hospitalis or something like that. So I can't remember the exact name. I might be able to find the actual name later on, or someone in chat might actually be able to remind me about it. But if you're able to use that method, basically where you divide the numerator and the denominator by the highest power of s, it makes evaluating the initial values and the final value theorems a lot easier for you guys. So can I go over the steps for the practice question? Yeah, a few people in chat are saying basically Le Hospital's law or something like that. Yeah, basically once you do use that law, you're pretty much okay for evaluating these. So, is it this practice question in particular you're talking about? The same examples that we're showing in this lecture? I'm not sure about the indeterminate part, but I will check that back to make sure. Last slide. Oh, alright, okay. So, in solving for the steady state value of the output of the system, that means you're going to be evaluating this with respect to y of s. So, for the first part here, it's basically going to be where when you evaluate this, what, last slide? Okay, yeah, this is the last slide. So yeah, the first step here when you're evaluating this is basically you're going to be evaluating the limit as s tends towards 0 of s y of s accordingly, because you're trying to figure out the steady state value. So this is as t approaches towards infinity. So once you evaluate this accordingly for the steady state value of the output, when you're actually mapping this accordingly for x of t being a step change of 5 units, that means you're going to have to find the equivalent x of s accordingly on the Laplace transform table. And once you have that x of s, you can substitute this in accordingly here, and then you can actually evaluate the limit accordingly for the steady state value for x of t being a step change of 5 units. For this one in particular, you can assume x of s here is just going to be 1. So this actually makes evaluating the steady state value here a lot easier for you guys. Hopefully that was the last slide you were referring to. If not, please let me know. Okay. Yeah, so this basically is the end of the initial and final value theorem. Are there any other further questions regarding the material of this lecture? Alright, so seeing that we don't really have any further questions at this point in time, we will be moving on towards the select questions from problem set 1. Okay, so let me see which questions in particular you guys wanted, or you guys voted on. Might be able to pull up my learn here to get the live results. Alright, so if you guys can actually see this, These are basically the results of the people who answered the questions accordingly. So the highest requested question to do was question 11 here. Sorry, was question 11 here. Then followed by the second highest, which was question 7. And then we had a tie between question 8 and question 12 here accordingly. So because we have enough time here, I will do question 11 first, then question 8. Sorry, question 11 first, then question 7, and then I'll do question 8 and question 12 accordingly as of such. If I, it's supposed to be right. Okay. So question 11 basically was asking about the mapping of an actual car with a mass of m with the coefficient friction kf, and that we need to figure out what is going to be the differential equation mapping y of t being the position of the car and x of t represented the driving or braking force applied to the car at time t. Right, so let's see if I can get up a whiteboard here to actually show you guys how to do that mapping. So I'm doing some practice. Filing. Okay. Right, let's go. That's okay. So basically, this question relies on a little bit of physics, where friction here is basically proportional to your velocity. And in doing so, that means your k of f coefficient being proportional to your velocity can be mapped accordingly as kf of v, and velocity is basically the differential of dy dt. We also know that the force here is equal to your mass by acceleration. Oh, excuse me again, I gotta answer the door, someone's here. Yeah, sorry about that. I had one of the close construction people coming from my door. They asking a few questions. Uh, Earlier on, I did mention that there's some construction going on next door, so I might get some interruptions here and there, but I hope that they don't come back and interrupt me anymore at this point in time. No, that wasn't a spoon, man. Alright, yeah, so let's get back to the actual solutions accordingly. Okay, so that was that. Okay. Right, so from your physics, basically, your overall friction is basically proportional to velocity. And in doing so, that means your friction coefficient K of F can be multiplied by the velocity, and the velocity is basically mapped as dy dt from your problem. We also know that force is a product of mass by acceleration. So, in doing so, the net force on the car is equal to x of t minus the friction. So this is going to be x of t here minus kf dy dt. Now, because this is F equal to ma being your net force, m here is basically a constant, but the acceleration is basically a double differential of y, which is going to be d2y on dt squared. So this entire net force here is basically m d2y dt squared is equal to this resultant equation. And if we make x of t the subject of the formula, this is going to be m d2y dt squared plus kf dy dt. And that's how you actually obtain your x of t function from mapping the entire force of the car in a differential form equation. Now, I can assure you that a question like this, based on mechanical forces, will not come in any form or fashion in your exams. This is basically just a practice question to figure out how you can actually formulate a differential equation from a general purpose problem that may exist in everyday life. So this particular problem that you're seeing here based on mechanical forces will definitely not come in some sort of evaluation. You will only be tested on electrical stuff only with respect to this course. Right. Right, yeah. So that basically gives us our mapping of x of t towards y of t accordingly in a differential form. Are there any questions regarding this? I believe the coefficient of friction is dimensionless, but for all abstract purposes, we just basically represent this as K of F, as given in the question. And yes, the KFC guy is actually my display picture. It's actually, for people who actually watch the Bleach anime, it's Araki Kenpachi. That is basically Kenpachi representing KFC, Kenpachi Fried Chicken. No, but because it's dimensionless, we just basically treat it as a constant for our abstract mathematics case. I think he's basically asking the respect to if it's not being dimensionless. In this case, he's asking if the friction has some sort of force. Not force. The friction has some sort of units associated with it, but the friction basically doesn't really have much units. It's just basically a ratio coefficient. But like I said, for our abstract mathematics case, we just basically leave it as a constant inside here. Yes, well, after Bleach closed up, Kenpachi had to make a living somehow, so that's what he's doing in Japan right now. Alright, so basically because we treat the friction as an abstract here, this is actually how we obtain the mapping to get the net force on the car with respect to x of t and y of t accordingly. So the next question that you guys wanted to do, I believe, was question 8. So, you guys were asking about question 7 and question 8 in particular. And okay, yeah, I'll do question 7 first and then I'll move on to question 8. So we want to start with question 7 in A here in particular, which is going to be x of t is equal to u of t minus u of t minus a. And we'll draw what the signal looks like first and then how we actually differentiate this accordingly. So on a separate copy here. Okay. So I can clear this. Because it's saved on video for anyone who needs to review it later on. So our question basically asks for x of t equal to u of t minus u of t minus a, where a is more than 0. So if we draw our u of t signal, it's basically our unit step. And because we know a here needs to be more than 0, that means a here is going to lie somewhere on our positive time axis. U of t minus a is basically a shifted unit step towards the right hand side because it's t minus a. So if we represent this by our green line, yeah, this would be flat here. That's going to be u of t minus a. So if we want to actually subtract the two signals, We want to actually observe this accordingly with our figure above here. So if we observe what happens here before 0, this is basically 0 minus 0. So our result here just be 0. And between 0 and a, on the other hand, this is 1. And this here is 0. So the u of t value here is 1, but the u of t minus a value here is 0. So we get a result of 1 minus 0 equals to 1 in between 0 and a. And then from a onwards, both u of t and u of t minus a is at the value of 1. So this basically is going to result in 1 minus 1, giving us a value here of 0. Oops. Now if we differentiate this in particular, we're now to ink at this point in time, so I just want to stick to a red line at this point. Basically, we're watching for what happens before 0, at a, and after a. So before 0 in particular, this is just basically 0. And if you differentiate 0, you just get 0. However, at 0 here, we have this sharp change from 0 to 1. And that basically, because we have that change, if we differentiate that change, that gives us a unit impulse. So at 0, we draw our unit impulse accordingly with a magnitude of 1. And between 0 and a, we have a constant value here of 1. And if we differentiate a constant, we basically get a value of 0. At a, on the other hand, we have a change from 1 to 0. And if we do the differential for this, this basically is going to be a negative impulse here, with a magnitude of minus 1, representing this change from 1 to 0. And that basically gives us the differential for the question. So these vertical changes here at these instantaneous time values, when you perform the differential on these are basically impulses. And we saw this in lecture 4, lecture 5, which we did last week in particular, that if we differentiate any of these sharp changes here at the instantaneous point in time, it's basically just going to result in an impulse. If you have to write this mathematically, this will just be delta of t plus delta of t minus a. Sorry, not plus, minus delta of t minus a. Because it's a minus 1 at that point in time. And the reason how we obtain the magnitudes here accordingly is because we had a change from 0 to 1 here in the upwards direction, and the upwards direction is treated as positive. So that's how we can get a magnitude here of positive 1. And then for the second part here, we have a change from 1 to 0 in a downwards direction. In a downwards direction here. As of such, because it's a downwards direction, this is a negative change, and the change in this value here was also 1. So we map this as a negative change of minus 1. So because we have an upwards change here from 0 to 1, and the change in value here is 1, this is a positive value of 1. If we have a downwards change, and this is going from 1 to 0, this is going to be a downwards change here, going towards negative 1 from the 0 axis. So this is actually for part A. Let's see what it is going to look like for part B. So part B is basically x of t here multiplied by t of the same initial signal that we had here, u of t minus u of t minus a. Let me erase a little bit from here down to part B. Oops. That's so basically, because we now want to have t multiplied by u of t minus of u of t minus a. This basically is just going to be our initial signal here, now just multiplied by t. And between 0 and a here, we had a constant value of 1, but everywhere else it was 0. So now that means that if we multiply by 0 here, it's still going to be 0. If we multiply by 0 here accordingly, it's still going to be 0. But 1 multiplied by t here is going to give us a ramp value here of t in between 0 and a. So what our signal now looks like is basically this. And because we know that the gradient of this line given by the equation that t, and there's no factor here in front, this means that the gradient must be 1. So our value here must be a in order to represent this gradient of 1. If we do the differential for this, if we differentiate this line here accordingly, and we know its gradient is 1, basically we'll end up with the result being the gradient. So as of such, between 0 and a, the differential is going to be 1. At a, on the other hand, we had a change here from a to 0. Oops. Because we have that change there from a to 0, that's a negative change because it goes towards in the downwards direction. And then we have an impulse here of magnitude negative a occurring at a here. So if we had a value of 3 in front of the t, that means now that we need to make sure that the gradient of the line is going to be 3. Now, in calculating the gradient of this line here, it's basically the change in y divided by the change in x. So the change in y here was a minus 0 divided by a minus 0, basically give us a gradient of 1. But let's say if we had it a value of 3 in this particular case, I'm going to make sure that we obtained a value of 3. This comes like we just say delta of y divided by delta of x is equal to 3a divided by a. And the a say will just cancel to give us a value of 3. As of such, in that case, we just only need to map this being 3a on the y-axis. To map this accordingly with respect to the gradient. Alright, so that answers part B of that question in particular. Anything that needs to be resolved at this point in time regarding this? So yes, it only changes on the y-axis because the change in x here remains the same. And yes, there is a jump in the graph at the impulse, because impulses must always start at the 0th line for the t-axis. So it must always start on this horizontal line here, representing the t-axis. Impulses cannot be suspended from some arbitrary value accordingly. So it can't be like, you can't have an impulse going like this, you can't have an impulse going like that. That's wrong, that's wrong. It must always start at this axis here, on the t-axis. Yeah, sure, I can explain what that is. So, if we actually do the differential of this line here, this is basically obtaining the gradient of the line. So the change in y from this point here to this point here, we're considering this part here being our endpoint, is that the change in y here is e to 0. So that's a minus 0. And the change in x here is a from 0. So that's a minus 0 as well. A divided by a will just basically give us a gradient of 1. So that's how you end up with a line here of constant value 1. So just basically the differential of the straight line here to obtain the gradient of the line, which maps as the differential accordingly. So yeah, basically it's because we had the difference of the unit steps there to obtain our rectangular signal. Because we multiply by t here, because the magnitude here was a constant value of 1, that means it's just 1 multiplied by t here to obtain a line here represented as t. So this straight line here is basically y equal to t, if you want to say it in this case. And the gradient, because it's t and there's no coefficient factor in front of the t here, is just going to be 1. And then when you do the differential, it's basically the differential of this line here, and then the differential of this vertical change here accordingly. And that's how you get the differential here mapping the gradient of this line, and then the differential mapping this vertical change at time e. And because it's a change from a to 0, the magnitude of this impulse here is going to be minus a accordingly. Alright, so I don't think we have any further questions regarding part B. Let's see what part C was all about. So part C was basically our signum function here. So I'm going to draw this out and then I'm actually going to differentiate this accordingly. So this is basically was x of t is equal to 1 at a more than equal to 0, and then negative 1 at a less than equal to 0. So this being our signum function, let's say, just for simplicity's sake, our value of a was at t equals 0. Let's say a was equal to 0. And our equation here was that it needs to be 1 for a more than 0 and negative 1 for a less than 0. One here and negative 1. Whoops, it draws on a different line, color line for you guys to actually see this. And then, because it connects at the 0 part here, we have this vertical transition representing our signum function. So this was x of t equals 1, 1 and 0, minus 1. Let's check this back just to make sure. Less than 0. Signum. So that's actually how you draw the signum function accordingly. If we differentiate the signum function, so if we watch on the left hand side here, before 0, because we're saying a equals to 0 here, it's basically going to be that before 0 we had a constant value of negative 1, and if we differentiate a constant, it's just going to be 0. So it'll be in a 0 line here. However, at t equals 0, we have a change from negative 1 to positive 1 in an upwards direction. And this change in value is a magnitude of 2. So that means that we need to draw a an impulse here. the magnitude of 2 representing this change. And then for t more than 0 onwards, we just had a constant value here of just 1. If we differentiate the constant, we basically just get back 0. So this basically is going to be the answer for our signum function, where if we say basically a here, it's going to be 0. So just to make things a little more clearer, this comes like if we just, right? What is it doing that? Right. This comes like instead of we saying a is more than 0, there's like t here is just replaced by a. So I believe, yes, there was a problem here. This is actually supposed to be t, not a. So that's the problem with this question in particular. So I'll change this accordingly on the problem set. What's the comments here? Sorry, I need to change this. Change a to t clarification. Right, so that way I know to change that accordingly when I put up the revised problem set. Yes, so a here actually needs to be t, because we're talking about respect to x of t. And in this case, we watch such that there's going to be 1 here for t more than 0, and -1 here for t less than 0. So in doing so, that's going to represent our +1 here for t more than 0, and -1 here for t less than 0. And then these 2 points here are connected by this vertical change for the signum function. When we do the differential, before time equal to 0, our magnitude here was -1, and the differential of a constant being -1 would just result in 0. At time equals 0, we have a vertical positive change here from -1 to +1. So this change in value here is 2. And because it's going in the upward direction, this is a positive change. So you represent this as a positive impulse here with a magnitude of 2. And then after time equals 0, this part here was a constant value of 1. And if you differentiate a constant, you just get back a value of 0 here accordingly. Right. So that basically is supposed to be the end of question 7. Yep, that's the end of question 7. So are there any questions regarding part C here in particular? So yes, mathematically it will be 2 of delta t. Parts A and B, let's check back. No. For parts A and B, these A values here are correct. For part C here, this is actually going to be t more than 0 and t less than 0. So parts A and B are correct, just part C here. For part... Okay. It's just only for part C that it needs to change. This is the only error here in the problem set. Now, one thing to note, there are some cases, like when you do get transform tables and you define the signal function, they do refer to this as A. So they will say like A more than 0 and A less than 0. But just remember, this just means T more than 0 and T less than 0, because the left-hand side here is with respect to T. Alright, okay, so the next question, because it's right next to this, it's going to be is question 8. So these is basically, we need to classify these differential equations, whether they are time variable or time invariant. So time variant or time invariant, we basically need to indicate the time variable terms. Alright, so alright, so a shortcut method for determining if these equations here are time variant or time invariant is to see if any of those terms here in the equations depend explicitly on t. So for question 1 here, this is a differential, but this is basically this is like y double prime of t, and then this is going to be plus 2y here equal to 0, and as of such, there's no component here that's being multiplied by t on the numerator accordingly. So this one here is going to be time variant, if I am saying that correctly. Let me just verify this. No, this one here is going to be time invariant, sorry. So part A here is time invariant because there's no explicit t being multiplied by any one of these components here. So part A here, sorry, is time invariant because none of these components here is being explicitly multiplied by some t factor. Part B, on the other hand, because this is a differential of t squared y, this means that you have a t squared here, which is independent of all the other components, and it's being multiplied, so this here is going to be time variant. And I'll explain why this is the case for part B. Just making sure one thing here before I explain part B in particular. Right. So part B is d dt of t squared y. Right, it's saying basically this is equal to 0. But when you do the differential for this, this being a product differentiation, this will resolve into 2t of y plus t squared dy dt equals to 0. And if we factorize out a t, or we just divide the left hand side on the right hand side by t, we get 2y plus t dy dt equal to 0. And because we have this t factor here, that basically means the equation depends on t. So the entire equation here is time variant. So once you have that t component here inside the equation, and you're unable to get rid of it, that means the entire equation there is going to be time variant. So that will be covering it for part B accordingly. So just to recap, this being d dt here of t squared y, this is a product differential. So that means we need to differentiate the first term here, which is going to be 2t multiplied by the y term here. And then we keep this term here being t squared constant, and then differentiate the second term to get dy dt here is going to be equal to 0. If we factorize out a t component here, or we divide the left hand side and the right hand side by t, you'll get 2y here from here, this part, and t dy dt equal to 0. And because we have this t component here in the equation, the entire equation here basically relies on this t component. As of such, the entire equation is going to be time variant. Let's observe this for part C now. So part C is basically 1 on t plus 1 d squared y dt squared plus 1 plus divided by t plus 1 y equals to 0. So let's actually write this out on the whiteboard for part C. Oh, before I go on, are there any questions regarding part B in particular before I go to part C? Alright, it doesn't seem like we have any questions for part B, so I'll move on to part C. So part C was 1 divided by t plus 1 of that. Okay, so write out this equation here for you guys. Let's verify this again. Y is equal to 0. So for part C, if we multiply both sides by t plus 1, our resultant equation becomes t squared y dt squared plus y equals to 0. And there aren't any explicit t components here. So this means that the equation here is time invariant. So in general, the trick is just to make sure if you're able to get rid of any explicit t components that may exist within the equation to determine if it's time variant or not. Oh, oops. This. Stay there. Right. So yeah. Since we have a 1 divided by t plus 1 component on the left hand side of the equation here, and the right hand side of the equation here is 0, if we multiply both sides by t plus 1, this means that these components here just resolve to 1. As such, we get rid of those t plus 1 components entirely for the entire equation. Because there's no explicit t multiplied by each one of these components here, this means that the entire system here is going to be time invariant. Or once there's an explicit t multiplied by any one of these components here within the system equation, the entire equation now becomes time variant accordingly. Right. And for our last question in part 8 accordingly, we have d to y dt squared plus cosine of ty equals to 0. There's no way to get rid of this cosine of t, unfortunately. If you try to divide it out, the cosine of t will now appear on this differential form here. If you try to do any other thing, it's going to appear somewhere else in the equation, so you're unable to get rid of this cosine of t. And as of such, this means that this equation here is going to be time variant, because cosine of t basically depends on that t variable. So that basically is the end of question 8. Are there any questions regarding this for time variance and time invariance accordingly? Right. Okay, so there doesn't seem to be any questions regarding question 8. The last question we'll be doing in the problem set here is going to be question 12, which is basically to sketch the derivative of the signal shown in figure question 10. So we're going to be deriving the derivative here for this figure in particular. So let's draw axes to start with. And we just now observed here that our axes are going from -2 to +2 on the time axis. So we have to split this accordingly. Right, okay, so that works. So let's draw our axes here. We'll say this is going to be 1, 2, 0, minus 1. And we need to perform. Hold on, let's make sure. We're doing question 12 in particular because that's what people voted for on the poll. If we have time, I can do question 10 as well to show you guys how to do the shifting signal. But basically, the solutions I'm going to post up is going to give you all the steps for question 10. So yeah, we are doing question 12 as it being indicated in chat, but we're just using the diagram from question 10 here accordingly. Alright, so we need to obtain the differential of this signal here seen in figure question 10. So the first thing that we observe here is that we have a change at t equals -2 from 0 to 1. And this change here, so I'm going to have to put values here on the y-axis. So because we have a vertical change here, accordingly, going from -2 at t equals -2, going from 0 to 1, this is basically going to be an impulse here with a positive magnitude of 1. In between t equals -2 and t equals -1, we have a constant value here of 1. And if we differentiate that, that's just going to give us a value of 0. In between t equals -1 and t equals 0, we have a gradient line here. And basically, the differential of this line here will give us the resultant gradient. So we need to figure out what is going to be the gradient of this line in order to figure out how do we put our differential here accordingly. So we can see here that the change in y, if we assume here is 1, it's from 2 to 1, so that's going to be a positive change here because it's rising upwards. So the change in y here, which we can say is delta y, is 2 minus 1. And then the change in x, because we're going from -1 to 0, this change here is a value of 1 in time instance. So this is just going to give us a resultant of 1. So the gradient of this line here is 1. And that basically is the differential of this line. The differential of this line results in the gradient. And we calculate the gradient here to be 1, so we just draw a vertical line here, a horizontal line here accordingly to represent this gradient. Now, at t equals 0 here, we have a change here from 2 to 3. And this change here is a positive change. Meaning, as of such, because we have a positive change here, we need to draw an impulse, a positive impulse, with a magnitude of 1 at t equals 0. So we draw this impulse here accordingly to show this. From t equals 0 to positive 1, we have a constant value here of 3. And if we differentiate a constant value, we just get a value of 0. So we draw this 0 line here accordingly. So I'm going to have to erase this part here, because I'm going to need space for our plot. For the next part. So at t equal 1, we have a negative change from 3 to 0. So the differential of this is going to be a negative impulse with a magnitude of minus 3 accordingly, representing this change. In between t equals 1 to t equals 2, we have a falling line here, which indicates a negative gradient. So we need to figure out what this gradient is going to be. So the change in y here is from 0 to negative 1. So that represents our change in y here, meaning that it goes to negative 1 change. Our change in x here is just going to be 1 time unit. So that's going to be negative 1 divided by 1, which gives us a value of negative 1. So the gradient of this falling line here is negative 1, and we just represent this accordingly as our differential value. And then at t equals 2, which is going to be the final part of our signal, we have a positive change from negative 1 to 0. So that results for our differential as a positive impulse with a magnitude of 1. So this will be the resultant of the differential of the figure question 10. Alright. So are there any questions regarding this differential of figure question 10? I have a question asking, do we have to assume a value like what we did to find the gradient of the first line, or would they normally give it to us? Normally we do give you all the values on the x and y axes. If for some reason, if it is missing, you can either assume a value, most of the cases it will just be like a positive value, or you can ask one of the invigilators for rectification, and the invigilator will approach us with the question, and then we will just say, okay, well, that value this needs to be either 1 or 2 or something like that, and it will get back to you immediately. So it's okay if you actually write in on the paper, like, okay, if for some reason the value is missing, assuming a value of 1 is here, or assuming a value of negative 1 here, and you go forward with that, that's perfectly fine. But it's also kind of important to notify the invigilator in the event of a final exam of this error in the question paper, so that way it can be circulated towards everyone in the examination itself. But yes, most of the cases you will get clearly labeled diagrams that won't be missing these things. Any further questions at this point in time? Alright, so looks like we don't have any more further questions. So that basically brings us to the end of our session today. And I will post up the solutions for problem set 1 accordingly on my learning. And any of the other corrections I need to make as well, I will also post them up accordingly for regards to the problem set and the lecture slides as well from the feedback you guys gave me. Thank you so much for that feedback. And it actually helps for us to review the lecture slides and the problem sets to correct any errors or any points that require more clarification out of such. So thank you very much for those feedback accordingly. And next week, our lectures that we're going to be doing in particular, we're going to be starting the important topic known as convolution. The convolution topic is actually extremely important because it forms the basis of how your signals operate with respect to any system in the time domain. And it is quite important to ask any questions during this convolution topic for any points that you are unclear about. Because there are certain points in convolution that you can get easily tied up on or you can get easily confused. So please make sure and ask questions if you are confused about anything during the convolution topic. Alright, and then in particular, after we do the convolution topic, we will start the first and second order system lecture as well. And that should bring us to the end of the lectures for next week. I will see if we have covered enough material for problem set 2. If we haven't, I will not put it up until we actually have covered the material. And then I actually will put it up and then we'll organize accordingly to vote on questions and so forth, as we did similarly for problem set 1. So, until next week, take care and be safe, and I'll see you guys soon. Later.